So this video will check out a pretty tough problem from the 2009 Form B of the AB exam. This was also on the BC exam. So this problem was one that overlapped across both exams. And it's tricky because it involves a lot of things that we've done, but we don't necessarily like to use a whole heck of a lot. If you read the setup here, we've got a continuous function f. It's defined on the interval -4 to 6. And the graph consists of a line segment and a curve that is tangent to the x-axis at 3. We've got the graph of it over here, so here's the line segment, and then here's the curve that would be tangent to the x-axis at 3. On the interval 0 to 6, f is twice differentiable, and f double prime of x is greater than 0. So in part A here it says, is f differentiable at 0? Use the definition of the derivative with one-sided limits to justify your answer. Well, I have this copy and pasted into the file here, and we'll take a look at this real fast. This is something that we definitely have used previously in the year. We just haven't had a need for it since we developed the product rule, the chain rule, the quotient rule. We have much more efficient ways to take derivatives now, but the definition of the derivative is right here. The definition of the derivative is this limit. The limit as h approaches 0, f of a plus h minus f of a over h. And if this limit exists, we say that the function is differentiable at a. Now we want to determine if our function here is differentiable at 0. So f prime of 0 would be, using the definition that's still right here, would be defined to be the limit as h approaches 0 of f of 0 plus h, right? I'm just putting 0 in place of a, minus f of 0. 0 goes in place of that a from the definition as well, and that's all over h. Now we don't really have the capability to evaluate this limit from this graph, but I'm going to shrink this back down. We kind of took what we needed from the definition. The way that this problem is worded here says we should be showing that doing something with one-sided limits to justify our answer. Now, I think we know the answer to this question without necessarily using the definition. Should this function be differentiable at 0? Well, I mean, at 0, the slope of the tangent line changes instantly from a positive slope to a negative slope. So we have a cusp point at 0. So we know that the answer to part A here is no. We are not differentiable at 0. Not differentiable at any point on a graph where you have a cusp. Now, how do you use this definition of the derivative to show that? Well, if you think about the one-sided limits here, meaning we'd be approaching 0 from the smaller side, and then also approaching 0 from the bigger side. Same expression within both limits. If the one-sided limits don't equal each other, then the limit itself doesn't exist, and since this limit defines the derivative at 0, the derivative at 0 wouldn't exist, and we'd not be differentiable at 0. So what we should try to be doing here is we should be trying to show that these one-sided limits don't equal each other, and if we can successfully do that, we're going to be able to use that as justification that the derivative at 0 does not exist. So as we approach 0 from the smaller side, so that'd be a number like -0.1 going in place of this h. So if we put a number like -0.1 in place of h, excuse me, think about what f of 0 plus -0.1 amounts to. It amounts to f of -0.1. Well, f of -0.1 is going to give us a y value that's about right here. Now, if you remember where this definition came from, this definition came from the formula for slope, difference in y values over difference in x values, and what we're doing is we're letting our difference in x values approach 0. At a value right here, what would the slope of your tangent line be? Well, the slope of the tangent line, or the value of this limit as we approach 0 from the smaller side, would be whatever the slope of this line is. What's the slope of this line? I think you can compute that. We have a rise of 1, 2, 3, and a run of 1, 2, 3, 4. So the slope of the line segment from this point to 0 is going to be equivalent to the slope of this whole entire line segment, which had a rise of, what do we say, 3 and a run of 4. So we'd have a left-sided limit of, whoops, accidentally put the run in the top. we'd have a one-sided limit from the smaller side of 3 over 4. Now on the bigger side, it's not going to be quite as easy. If we put a value like positive 0.1 in place of h, that would give us a value that's, just about right here on the curve. And if we look at any of the little line segments that would be positioned up here on the curve, all of those line segments are going to have a negative slope, right? So all of those line segments are going to have a negative slope. We don't know what the numerical value of this one-sided limit is, but we can definitely say that it's going to be negative. It's going to be less than 0. Because this value is going to be negative and this value is positive, the one-sided limits don't equal each other. Therefore, this limit does not exist. And that's how we know that our function is not differentiable at 0 based on the definition of the derivative. We'll do the other pieces of this in separate videos.